Okay, so the problem with the transform and what you're going to kind of see is it seems somewhat magical, like it just works, and it's super great that it works and you'll use it, but you probably or most likely it's going to be kind of a little foggy as to what's going on actually. So I wanted to help reduce some of that fog. So what we're going to do is discuss what a complex function is, because that's what a transform is. It's a complex function. The S domain takes in complex numbers and outputs complex numbers. And then I'll show you how you can use the transform to predict sinusoidal and exponential behavior. And in particular, we can use it on the mass spring system to predict, the different types of motions: critically damped, overdamped, underdamped, and harmonic motion. Okay. So look, if you remember in example 2, we proved this. We proved that the Laplace transform takes this function in the t domain to this function in the s domain. The f function is a real function. And what we mean by real function, this is all the functions we've ever worked with, really. It takes a real number to a real number. Okay, so it's really easy to visualize these things, because essentially what we do is we plot two real axes, right? You have your input real axis, and then you have your output real axis, 90 degrees. And then if you have, if you plug in, let's say a 3 and you get out a 7, you go 3 in the input and 7 in the output, and you plot the point. And then you plot all the points and you end up getting this curve. So those are super easy to graph. For example, if you wanted to graph this function, we've been doing it so long, you could graph it in Desmos or do it yourself. Let's say we graph this function on 0 to infinity. It looks something like that. All right, but what about this one? We haven't really discussed this yet. Let me smack my cat. Give me just a second. She's being really annoying. Hey, stop it. Stop. Okay. All right. Okay, so this guy over here, that's the transform. So what's happening there? So here's our transform. Now, up until this point, we've been kind of assuming that this is a function of a real number, but it's not. It turns out S is not a real number. It's a complex number. So what I'm saying is that the S domain, or the Laplace or Laplacian domain, is complex. It's a complex. It's in the set of complex numbers. So if you remember from algebra, the way we designate a complex number is by writing it this way. We write z equals a plus bi. So there's a real part, which is this part, and then there's the imaginary part b in front of the I, which is called the imaginary part. So in order to graph these things, you need two dimensions. You need one for the real part, and you need one for the imaginary part. So typically what we do is we graph this in what's called the complex plane. All right, so the complex plane is another kind of a Cartesian looking system where you have a horizontal axis and a vertical axis. And so for just a single complex number, what you would do is you'd go on the real axis for your real part, and then your vertical would be your imaginary part. So if we had the number like, let's say 3 plus 2i, we would go 3 in the real, up 2 in the imaginary, and then we'd plot our point. Okay, it requires two dimensions to graph a single complex number, and that's difficult. That's unfortunate, because for reals you only need one dimension. So so we do this in the complex plane. Now here's the thing though, if you have a function that takes a complex number to a complex number, you need one plane for the input, and then you need one plane for the output. So we got two dimensions here for the input, and then we've got two dimensions for the output. That's a total of 4 dimensions. So for us to try and combine that together into a single graph like we did up here, it's impossible, right? Because a real to a real, that's only 2 dimensions. But for a complex to a complex, that requires 4 dimensions. So one way to do it is to keep them separate, like I show here. So what I've got here is a function, a complex function, which maps a complex variable to a complex variable. So watch what happens as I move this dot. So I want you to watch the output variable here. Okay. So that would be one way to visualize a complex function. The problem is it's not very intuitive at all, right? It doesn't really tell you much about what the function is doing. It just seems like the output dot is moving around randomly. So it's not very helpful. And the whole point of a graph is to get something that's helpful. You can figure out the general nature of what the function is trying to tell you. So it isn't helpful. So fortunately, there's some mathematicians, over time that have kind of figured out ways that we can take something four-dimensional and somehow come up with different ways of trying to visualize it. And there's two ways we're going to talk about. One of them is the real imaginary plot, and the other one, the more interesting one or fun one, is the 3D plot. All right, so let's start with the real imaginary plot. Okay, so for the real imaginary plot, what we're going to do is we're going to keep the input variable in the complex plane. We're going to keep it there. It's the output variable that we're going to mess with. So we're going to use the complex plane. Now let's look at the output variable. The output variable, that a plus bi, that complex number, what we're going to do is represent that number using color. Okay, and there's two facets of color that we're going to focus on. One of them is hue, which is kind of like it's kind of a gradient between colors, so hue. And then the other one is lightness. And you guys know how to do, if you have light brown or lighter brown, you guys know what color that is or kind of what it looks like. And so those are going to be our two dimensions, hue and lightness. So now in order to make this worthwhile, instead of looking at our output variable as a plus bi, we're going to convert the a plus bi to a polar representation. And you guys have done this before. We've done lots of polar stuff. So basically, if this is your number, a plus bi, what we're going to do is we're going to find the distance from the origin here out to our point. That's called the modulus. And then we're going to find the angle off of the positive real axis in the counterclockwise direction. And that's called the argument. We're going to map both of these. Let's see, the modulus is going to get mapped to lightness, and the argument is going to get mapped to hue. That's the big idea. So let's take a look at what's going on. So I'm just looking at the output variable for right now. Now, let's start with the modulus. So so let's talk about hue just for a second. So the way you set this up is using a color wheel. So what I've got here is a color wheel, which is just telling us how to assign the different hues and brightnesses for each complex number. So you'll notice that the colors, if you go around in a circle, they kind of change from like pink to yellow to green to blue to purple back to pink. So it's kind of rotating around like we see here and comes back to where it started. Same thing in our color wheel. The other thing to note is it's kind of hard to tell, but the colors are darker in the middle and they get lighter as you move out. Okay. In fact, if you go to the very, very center, you can't really see it very well, but it goes completely dark right at that point. And as we move out to the edge, it goes completely white. So this part right here is going to be the modulus of our complex number. It's going to be the distance from the origin. That's going to be that representation. And the angle at which the angle at which the complex number sits will determine the color. So in this case, it'd be like green. Okay. I'm sorry, not color, hue, right? For a smaller modulus, in fact, when the modulus is 0, that's a complex number of 0 when it has no length. What's going to happen is your lightness will go completely dark and it's going to go black actually. So these are what we call the zeros of the function. And I'll explain why in just a minute. And as the size of the number gets larger, the size, I mean this distance, it'll go all the way out to the edge. and that'll approach a whiteness. And it should approach eventually, well, it'll tend towards getting lighter and lighter and lighter. Okay, so at that point where it goes infinite white, we call that a pole. All right, so let's take a look at an example. All right, so here's a function. We were using an S earlier, but typically we use a Z. It's just for the transform, we use an S typically. But for complex variables, for real variables, we use an X. And then it's standard by convention, we use a Z for complex variables. So that Z right there is representing an A plus BI. All right, so what you would do, this is called a real imaginary plot. You have an input variable, which is complex in the complex plane, and an output variable. The input variable is in the complex plane. Do you see the complex plane there? Real axis, imaginary axis. Now what I'm doing is I'm moving this one on top of this one, but I'm not using a physical plane. I'm going to use color and hue and lightness. So you'll notice at every point in this plane, there's the hue and lightness is kind of changing a little bit. All right, so over here on the right, I've got two scales. I've got a scale on the left, which is giving me lightness. And I've got a scale on the right, which is giving me hue. And notice the angles go from negative pi all the way up to pi. That would be one complete revolution. You can actually see it right here. This one starts to turn blue here, and this one starts to turn green there. That would be all the way around the color wheel. Okay, so the interesting parts about these graphs are really the poles and the zeros. So the poles are the points where you see black spots, and then the zeros are the point where you see black spots, and the poles are where the points where you see white spots. So when I look at this graph, I don't really see any zeros. I don't see any kind of concentrations of black spots, but I do see a kind of a concentration of a white spot. Do you guys see it? Right in there? Probably hard to see over Zoom, but yeah, it's definitely getting wider right there. So what's happening right there is we have a pole. All right, what a pole basically means, it means your function blows up there. So our complex function f is blowing up. It's getting very large. In other words, what that means is this modulus, the size of the complex number, is getting very large away from the origin. Okay. So yeah, so that's an example of that one. Let's see, I got another one here. All right. All right, so we can list off the zeros and the poles. So definitely there's no zeros because I don't see any black spots. And it looks like, let's look at the pole. Now this is in the complex plane, so you want to label it. It looks like the pole happens over here at -3 on the real and 0 on the imaginary axis. That's imaginary. So we have 0 or -3 plus 0i, which is really just the real number -3. All right, now let's talk about one that's more interesting because that one was pretty boring. Let's look at this function. This is another complex function. The fact that I'm using z means that it's complex. All right, this is what the graph looks like. All right, you notice we've got 4 dimensions here. We have the complex plane, which is 2 of the dimensions, which you can see. And then we have lightness and we have hue. And those are our 2 other output dimensions were associated with the output variable, the modulus and the argument, respectively. Okay, so now in this graph, we can get a sense as to what's happening with the function, which is the whole point, right? So what's happening here? Well, do you see any dark spots? If you look really closely, when the colors converge together, you should see some darker spots. So we've got a 0 right there. We've got a 0 right there. And we've got a 0 right there. Is that fair? Okay. Do you see any white spots? Yeah, we've got a pole there. And we seem to have a pole there. And they look to be kind of symmetric. And by the way, that'll always be the case for poles. They'll always be symmetric across the real axis. We'll talk about that in just a second. Okay, so let's list them off. All right, so for the zeros, you'd want to identify where they occur, right? Remember, this is the complex plane. So we've got zeros, we've got one there, 4, that's a real number 4. And then we've got one up here at 7i and one down here at negative 7i. So that's a complete list of zeros of f. Okay. What about the poles of f? Well, the poles are where the white spots occur. So you'd want to look closely, but it looks like that pole occurs at about negative 4 plus 3i. And the one over here, the complex pair, the conjugate appears here at negative 4 minus 3i. Okay, so we've got both poles and zeros. So I mentioned this earlier. Poles are when the function blows up. Zeros are when the function zeroes out. All right, now for the intuition part. Look, this is the function we started with, right? Now, if I asked you to factor the numerator and denominator, this is what you get for the numerator, and that's what you get for the denominator. You guys could do that. Denominator doesn't look like it could be factored nicely. However, that's not the end of the story. What you've done here is you factored over the real numbers. But if I allow you to factor over the complex numbers, you can factor further. In fact, you can factor all the way down into linear factors. Are you talking to me? I saw your mouth moving, but.
No, my sister was telling me that dinner's almost ready.
Oh, I'm sorry. Okay. Yeah, if you have to go, no worries. Okay, so if you look at the numerator, the s squared minus 49, normally you can't factor that over the reals, but over the complex numbers, we've got 7 minus i and 7 plus i. If you multiply those together, you'll get s squared minus 49. And if you factor the denominator using the quadratic formula, you get negative 4 plus 3i and negative 4 minus 3i for the roots. So those are the factors. But take a look. That's the function f, right? The zeros of a function happen when the top is 0, the roots of the numerator. Those are the zeros. 4, negative 7i, and positive 7i. The roots of the denominator are going to force the function to blow up, right? We all know when you divide something by 0, it makes the whole thing just blow up to infinity or negative infinity. So if you plug either one of these into the denominator, they blow up. Okay, so that's some intuition basically on what a complex function is, which is what a Laplace transform happens to be. Okay, so this is all fine and dandy, but it's really, I mean, it's cool looking, but it's kind of hard to spot. I don't know if you know, I mean, finding the poles, and it's really hard to see. So it would be nice if we could come up with another way of graphing it that maybe is a little more spatial. The problem is we only have 3 spatial dimensions. So what I'm going to do is I'm going to stick with the same complex plane for the input variable. And then for the output variable, instead of using hue and lightness for the modulus, instead of using lightness and hue for the modulus and argument respectively, let's take one of them and let's make it spatial. Let's take the lightness part, which is the modulus, and let's make that one spatial, and then we'll leave the hue as our 4th dimension. We're going to need that for the argument, so we have nothing left. So that's what we do here. Just so you know, here's what it's going to look like. This is the same graph above, but this time we're expressing the modulus spatially. And you'll notice if I look at it from above, it looks very similar to what we have before. Okay, but now it's almost more obvious when you see it this way that those are poles. Now, the zeros are not that great, right? It's still hard to see the zeros. So let's get to that in a second. So yeah, so the idea is, you do it spatially, and oh, I didn't have much to say there. So when you graph this thing, you'll notice that I've lost one of the scales. I don't have a lightness scale anymore. Now I just have a hue scale. That's the argument of the complex number. So we have to include color, but hue, but there's no lightness. Okay, so yeah, so the poles are super easy to see, which is very helpful. However, I can't really see the zeros very well, for the modulus. So, one way you could fix this is you could apply a log function to it. So if you think about the log function near 0 like stretches things out. the log of a small number goes off to negative infinity. So if I take the modulus and apply the log function, what you can do is you can make this thing look a little more helpful. You can still see the poles up top, but now what it's doing is it's stretching out the zeros. You see that? So now it's super easy to see. All right. And you'll notice spatially, we've got 3 dimensions, and then that 4th dimension, well, we still have to use Q for that one. That's the angle of the argument of the number. That okay? Okay. All right, so that's what a complex function is, and that's what a Laplace transform is. Okay, finally, we're going to use this fact. We're going to use what we know about poles and zeros and how they correspond to roots of the numerator and denominator of the roots of the numerator and denominators to see if we can gain some insight into what's happening, let's say, with the mass spring oscillator system. Okay, so let's take a look at the following table. We generated all these today. You know, we did 2 of them by hand, and the rest of them are in the table. So look, let's say, well, first of all, do you notice that these are all polynomials over there with a numerator? It's a rational expression with a polynomial in the numerator, a polynomial in the denominator. Every single one of them. In fact, all of the ones we work with in this class are going to be ratios of polynomials. Now, what I'm going to focus in on is the poles. Okay, so I'm going to take my complex function f. The poles happen where the denominator goes to 0. Another way to say that is the roots of the denominator. Okay, so we're going to be looking at the roots of these guys. So here's what ends up happening. You can use the poles to determine the general behavior of a differential equation. In particular, you can identify whether it's the solution is exponential or sinusoidal or a combination of both, just by looking at the transform. And what you're looking for is the poles. The poles will give it away. So, for example, we can look at the table we already have. Let's take a look at the pole for the first one. So remember, these are polynomials in S. So A is a constant. So the root for this first one would be S equals A, right? If you set the bottom equal to 0 and solved it, you get S equals A. Now, A is a real number. A, right? So at least for all the problems we're working with. So what's going to happen there if your pole is a completely real number, which it is in this case, A is real, S equals A is real, then what's going to happen is the motion of your system, whatever it is going to be exponential. So in terms of the mass spring system, if you go back and you think about the different types, right? We had overdamped, critically damped, underdamped, and harmonic motion. Okay. The ones that were exponential were overdamped and critically damped. Okay. So basically what would happen, what's happening here is that 1 over S minus A, that Laplace transform, is telling us that the solution to the system is exponential. It's an overdamped or critically damped solution. Okay. All right. What if the solutions are imaginary, purely imaginary? Okay. Well, that would correspond to these two right here. Now, the reason I say they're purely imaginary is look at the bottom, that polynomial in S. I don't care what you choose for B. Let's say it's 5. You got S squared plus 25. If you find the roots of that, what you'll find is that S equals plus 5i and S equals negative 5i. And 5i and negative 5 are completely imaginary. They have no real parts. Okay, so they're on the vertical axis this time. And if they're on the vertical axis, what you're guaranteed to happen is that your function will be sinusoidal. It could be a cosine or a sine or combinations of them. Sinusoidal, there's no damping with sinusoidal. It's just harmonic motion. So if you run across one of these and you're curious about the behavior of the solution, you know automatically that because the poles are on the vertical axis, the imaginary axis, you know the solution is harmonic, it's sinusoidal. Okay, and you get all this just from looking at the transform. Now, complex number, when I refer to complex, I'm referring to a number that has both a real part and an imaginary part. So it's somewhere not on the imaginary axis and not on the real axis, it's somewhere over here. So in this case, when we look at the poles, what's going to happen if you set that equal to 0 and solve either one, because they're really the same, what you'll always get a complex number every time. Okay, so what's going to happen here is you're going to have kind of a combination of exponential and sinusoidal motion. And it kind of makes sense because the vertical axis, imaginary axis, corresponds to sinusoids. The horizontal axis corresponds to exponentials. So if you're over here or over here, you should have some combination of the two. Now, in terms of the mass spring system, when we're working with exponentials and sinusoids, at least for real life problems, this is when we're working with underdamped motion, right? Kind of does this and tapers off. Remember, these had an e to the negative at times a sine function or a cosine, and they damp out over time. So that's corresponding to underdamped motion. Okay, so so this kind of brings up an important point. You know, when we're working with the Laplace transform and we're solving applications, we don't really care so much about these graphs. You know, about these, they're super interesting to look at, you know, and play with, and you can see the zeros and the poles. But really, the only thing we really care about as far as the behavior of the system is the poles. The zeros too, a little bit. We're not going to get into that, but the poles are the major part because they'll tell us whether our solution is sinusoidal, exponential, or both. Okay, so so because of that, and by the way, the zeros and poles, we call them collectively, we call them critical frequencies. These are where things, this is where things happen, right? At the zeros and the poles. Okay, so when the function goes to 0 and when the function goes to infinity. So we don't really need those complicated plots. So we could dumb them down into a very simple plot. It's called a pole zero diagram. So if we were to take this complex function and you factored it, the numerator and the denominator, and then you graphed the poles and the zeros, you can see right here in the numerator, we've got a 0 when z equals -1. So we got a pole there, right there. And then for the denominator, if you find the zeros of those guys, you've got 2 poles. And by the way, the poles will always be symmetric about the real axis because they appear in pairs. Is that okay? Okay, so now what we can do is now we can predict behavior. Okay, so let's say you have some unknown function f, and let's say this is its Laplace transform. So if we're dealing with the mass spring system, just looking at that, you can tell what type of motion you have. All you got to do is look at the denominator and determine where the poles lie. Are they on the horizontal axis? Are they on the real axis? Are they on the imaginary axis? Or are they somewhere over here? And then from that, you can tell what type of motion. So for this one, what type of motion are we going to have? Is it going to be overdamped? We're not going to overdamped and critically damped. That's one type. Or underdamped, or what was the other one? Sinusoidal. What do you think for this one? What's the root of the denominator?
It should be overdamped.
So this is s equals -3. Yeah, so it's e to the -3t, in fact, right? So you can actually jump right to the solution if you know the poles. So yeah, there's your pole. It's completely on the real axis, and like you said, it's overdamped. So the pole is -3. In fact, there's your solution, e to the -3t. And that's a mass spring oscillator with, it's either critically damped or overdamped. In this case, it's overdamped. Yep. Harmonic motion, for this one, same thing. You can just look at it. You can look at the roots of the denominator, see whether they're on one of the axes. If not, it's underdamped. So that'd be s equals ± 2i. So here and here. So it looks like this. Okay, those are completely imaginary, which means that our solution is sinusoidal or harmonic. So there's no friction here. Is that okay? All right. And yeah, and by the way, again, they always come in pairs because when you factor, they always, those polynomials always map out that way. Or here's one. Let's say you look at one of these. So all you really have to do is look at the denominator. And if you factor that, you're going to get, what is that? -3 plus or minus 4i for the solutions, for the zeros of the denominator. And those are in quadrants 2 and 3. So because of that, so up here, oh, it's also got a 0 right there. Okay, so this one's interesting because it's got the damping because it's got a 0 on the real axis. All right, so we didn't really talk about zeros too much, but and it's got this one, yeah, and it's got poles in the complex plane off the axis. So we have exponential and sinusoidal. So this is damped, or what would I say, under damped, really. Harmonic motion, okay. And lastly, you can also even use it for something like this. This has if you set the denominator equal to 0 here, find the roots, you get a double pole at 0, right? And it's real. 0 is a real number. So you get a double pole right there. So the double pole corresponds to the ramp function, f of t equals t. Okay, I didn't really talk about that earlier, but that's just kind of a special case. So the solution to this guy is just t. And all of these are in the table above, but it's kind of neat that you can get some intuition from behind it. So as you're working through the problems in the next few sections and you run across a Laplace transform, notice that it's a polynomial on top and bottom. The zeros on the top give you the zeros. The roots on the top give you the zeros, and the roots on the bottom give you the poles. And from the poles themselves, you can figure out the nature of what's actually happening in the t domain. Okay, I'm going to stop here.